Hello everyone, welcome back to another video installment on the Power of R tutorial series. This is video part 2b. In the previous video, we talked about the creation of data and the respective data types in R. In this video, we'll be going over the manipulation of data. So let's get to it. So in R, when we talk about data manipulation, it's very hard to run away from this concept known as vectorization of operations. So what exactly does that mean? As mentioned in the first video, most if not all of whatever you deal with in R is actually a vector. So vectorizing your operations means that you're basically using vectors to aid you in your operation. So that still doesn't answer much about what it actually is. So maybe I'll give an example. So for instance, on the right here we see we have a data frame with some values. These look like data from an experiment because there's a time column, there's a data column. So let's just say this is a very generic experimental data. So let's just say we wanted to perform operations on this data. So we wanted to, for instance, double the timing for some reason, or yeah, in that case, we wanted to multiply every single value in the time column by 2. We could actually do that directly without having to create a for loop to iterate through all the elements, unlike in other languages where you might have to do so. If you're not sure about what for loop is, do check out our introductory series to the art of code. That would provide a very good foundation. But in R, we don't have to do that. We can simply pass the entire column into our operation, and the R software will do the rest of it for us. So let's just say at the bottom here we assign training $time times 2 to training $time. Let's just say that $ is something that has not really been discussed, but let's just say it is used to reference columns. So data column name would mean the column that we are choosing the column name from the data. So that's just another nifty way to select columns other than the indexing methods that we have learned beforehand. So as you can see, we literally return a data frame where the time values are doubled. So that's something that's very interesting. We don't have to iterate through the entire data frame or the entire column. We can simply just pass the column as a argument to our operation, and it basically would perform the operation on all the elements in our vector, matrix, or data frame or column, the data frame column. You could actually do that for the whole data frame, but in this case we're doing it for the column. So apart from doing standard operations, vector operations, we can also use a function called apply, and this is a very useful function if you're trying to do something that's not so straightforward as simply simple mathematical operations on columns or rows. For instance, over here we want, let's say for example we want to find the sum of all the data in a column. We can't simply, there's no operation for sum, a mathematical operation. We can't do that using the standard method we've shown previously. In this case, apply functions are very helpful. A quick note here is that these apply functions are part of something which is known as base R. So since R is a very old language, there's been a lot of renditions, a lot of revisions to the code. But to avoid having everything fall apart, little of bit of the original R, as in the original R coding methods have been changed, and people have mainly written things over the R standard method of writing code. So we have something that's known as base R, and base R specifically refers to the original, unabridged version of R. So there are some functions which can only be called if we install external packages from the library manager, or so I say the package manager, but that's something we'll be going over in the later part of the series when we talk about specific packages that we will be using to make our life a bit easier. But this apply function is part of base R, so this means that you don't have to install anything. This works out of the box, so which is good for us because we are trying to get a little bit of a foothold into R. We don't want to work with too many packages. Let's just use this for now. So what does apply actually do? There are actually many variants of apply, not just the 3 listed here. There are actually a bunch of others, but I think these three should give you a good idea of what the rest can be able to do for you. Apply basically takes data in the form of a matrix data frame and returns the data, returns some form of data, not the same type of data, in the form of a list, array, or vector. That's the basic idea. It is a function that takes data and returns another type of data. So it's something like what we did where we put in data and we put in data into a simple mathematical operation and it returned another set of data. So that's the idea. lapply basically is similar to apply, but instead of returning data in form of a list array of vector, it only returns data in form of a list, whereas sapply returns data in form of a vector. So a thing to note here is that in all cases, the length of the output vector slash list must be the same or will be the same as the length of the argument supplied. So for instance, yeah, I think it just speaks for itself. So let's move on. Okay, so what exactly does apply do? So for instance, the basic functionality of the structure of the function is apply data margin equals 1 or 2 or C1, 2. This just means, okay, we'll go over what this means later. So as of now, the data refers to the data you want to apply on, whereas margin refers to the columns or rows. So if we put margin equals to 1, that means we're choosing rows, and if we put margin equals to 2, we're referring to columns. If we put C1, C bind, the open bracket 1, comma 2, this means that we are selecting both columns and rows. And function refers to a function we will apply to the elements defined in the previous argument. So, example, let's say we want to find the sum of the values in our previous data table, the training data table. We can use apply, so we call apply, data is training, and we will choose to operate on the rows. So we will put 1, margin equals 1 or 1, that works, both work as well. And we will choose our function. So there are some built-in functions in this apply, such as sum, such as, if I'm not wrong, there should be one that gives you the max, I think. I'm not too sure. You can refer to the manual page or to the documentation for this function. So this basically returns us the sum of each of the rows, and since, as I mentioned previously, that the length of the vector or list returned will be the same length as the number of rows slash columns, so we here see that this returns a vector of a length the same as the number of rows, because it makes sense. Since we are summing the rows, we should have a number of data entries that's the same to the number of rows. Doing the same thing to the columns by putting margin equals 2 gives us, as expected, vector of length 2, because we only have 2 columns. So yeah, once again, this pretty much explains it. Not only can we do manipulation on data frames or matrices with numeric or numbers, we can also do it with string. So how that works is that we have, for instance, over here, we are applying applying a function called toLower on a training tool, which is essentially just a matrix with some text in it, and we are choosing to both columns and rows. So toLower is another function that basically changes the matrix, changes the characters in data frame or matrix to lowercase, and that's the power of apply. It can do non-mathematical operations as well as mathematical operations. Similarly to apply, we have list apply or lapply. In this case, we see that when we did the same thing to training 2, it returned it as a list. So apart from the data type that is returned, pretty much similar functionality there. For sapply, similarly, returns it as a vector. So I think it's kind of self-explanatory once you get the rough gist of what apply does. Extending it to different cases and different the other types of apply is also kind of simple. So let's just say we want to pass a custom function to apply. That's also possible. So over here we see we have defined a function, and it basically is going to return 2 times whatever argument you pass to it and add 5 to it. We apply this function to the training data, and we see that that's exactly what happens. It applies this function to both the columns and the rows of the training data. So that's all fine and cool, but what if we want to select data based on its values rather than based on its position? So far we've used apply, which basically just blindly applies, as the name suggests, functions to its rows and columns. But what if you want to select and kind of be like filter out data based on its value? So that's when Boolean indexing comes in. So what is Boolean indexing? It's kind of an interesting concept. I will do my best to explain it, but feel free to pause the video as and when you think that you're getting lost, and or perhaps repeat it and see if we can get it done together. So let's just say, as we have learned in the previous series, or perhaps at the start, that a Boolean is the kind of like the simplest value or simplest data type in coding, where you have only two states. You have only true or false, 1 or 0, on or off. So we know that we can use what we call comparison or logical operators in, for instance, if statement. Look at this over here. We have if x is larger than 0, run some code. So what this statement x larger than 0 evaluates to a Boolean, because this can either be true or false. There's only two states. And then if basically takes that argument. If this is true, it runs. If it's false, it skips it. That's all fine. I think we're very clear with that. So we can use this logic to not just perform if and if-else statements, but we can also perform actual indexing and apply this to entire data frames. That is the idea. So let's just say we have a small data set that is going to be basically just 1 to 5, 2 to 10. And let's say we want to choose data that is smaller than 5. So, well, if we're using standard indexing, that would not be possible, because we would only be choosing like, oh, small data, open bracket, row, comma, column. This would be choosing a position. We would have no idea what the value of the position would be, for instance. So that is not a viable solution. Well, on the other hand, we can kind of take advantage of the fact that we know how to do, for instance, the logical / comparison operators, and we can take advantage of the fact that these basically return a Boolean value, and then use that to index the position of our data. So let me just bring you through. So for instance, if let's say we were to just dump let's say we were to do an if statement. So we say if x is more than 5, we will pass a value to x. X can be 1, 2, 3, 4. We return true, else return 5. Else return false. But we can actually dump the whole data frame, or should I say columns of the data frame. Okay, I should say whole vectors, not whole data frame. That we actually could but as I'll show you, it would be it would be better if we just dump vectors in to choose by column values. We can dump in the whole data frame as x, and that's similar to what we did at the start when we talked about how we could apply mathematical operations to entire columns rather than to single entities, because vectorization of operations is something that R uses. So if we were to simply just throw the entire data frame into our comparison logical operator, basically data frames more than 5, we would actually be returned a data frame that essentially has each of its entities corresponding to the outcome of the comparison. So if let's say this value over here, I can think of 1 is more than 5, true. 2 is more than 5, true. 3 is more than 5, true. 4 is more than 5, true. 5 is not smaller than 5, false. 2 is more than 5, true. 4 is more than 5, true. 6 is not smaller than 5, false. 8 is not smaller than 5, false. 10 is not smaller than 5, false. So essentially we have a data frame that kind of gives us like a readout of the outcome of our operation, which is kind of amazing, because we can kind of make use of this to do some things. It might not seem that obvious now, but let's just move on. So once again, if we want to be more specific, we could select a certain column. So for instance, small data, double square brackets, quotation, x is more than 5. Once again, this is another way to select columns together with the $sign. I mean, no stress, this isn't that important, but just so you know, this also returns us a vector of Boolean values corresponding to the outcome of this logical operation. So it basically does give us kind of a hint on what we should do. So now that we have a vector of Booleans which tell us whether or not our essentially whether or not our entry in that position is worthy of being selected or not, we can make use of that to actually just select it. So how do we do that? Well, in the first part we talked about indexing, and we know that we have to pass two values, basically a row and column, separated by a comma. But the indexing notation also accepts vectors that contain the Boolean indexing values. So for instance, if we were to put in a vector of length, the same length as the number of columns or rows, and it had true, false, etc., etc., it would select those which are true and omit those which are false. So this is essentially what basically allows us to make such clean and really like beautiful indexing. So let's just have an example. So over here, if once again we have our example where we took the result of this operation, the column x in data frame small data is smaller than 5. This returns us a vector with each of its elements corresponding to the outcome of this this operation, and we will basically now use our normal indexing notation to basically extract the data that we want. So by putting so we know that it's column comma row, right? So we put in row comma column, my error. Rows we don't put in a value, but we put in this vector which has the Boolean values corresponding to the outcome. We put that in, and comma blank, which means that we are selecting all the columns. So basically what that does is that it will return at the positions where this is true and not return it where it's false. This is something that is very clearly seen here. So for instance, we know that this would have been 5, and that would have not met this criteria, therefore it would be false, therefore it will not be shown. Similarly, if we do that for the rows, if we do that for column Y, we see that only these first two come out, because afterwards 6 is not smaller than 5, 8 is not smaller than 5. Therefore, this would have been true, true, false, 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 and that wouldn't have come out, and everything below the first two wouldn't have come out. So this is something that's very interesting. We are able to basically select based on value simply by using some pretty simple logical comparison operators that you would have learned in the first series, the art of code. And as mentioned, it's not only limited to simple inequality operations. You can perform the full range of comparison / logical operators. That includes and or not operators. Those are logical, modulo, somewhat that's a comparison. Inequality equals to, etc. It opens a real wreath of possibilities for you to explore and manipulate data using this Boolean indexing method. So now that we have gotten to grips on how to use the Boolean indexing in R, let's start doing something with it. So maybe if you have R opened or RStudio opened on your desktop right now, you can just copy this over into your console. This is just if you don't understand what sequence seq function is or sample function is, no worries, we'll cover it in a later video. It's not that important, you just need to be able to do the operations. Copy this over and you should have created a data frame with basically 100 rows and 2 columns. You can check that by just typing in challenge or print challenge. And now let's do some exercises. So let's choose rows where time is smaller than the value n, say n equals 20. Then let's choose rows where there's a multiple of a number, where time is a multiple of a number, say multiples of 3. And then let's modify rows by adding or subtracting a known value to the data column. So if you're not sure about the operations that you have to use, do check out the series on the art of code. That would be a lot of information there. And I'll just give everyone like 10 seconds before we move on. Alright, 10 seconds is over. Let's look at the suggested solutions. After all, there are no real solutions per se, it's just what I think would be the most straightforward. And these are some methods you could have used. So one important thing is that the operations that you perform are not saved to the variable until you actually assign it back. So for instance, if I would just copy and paste this into my console, I would not, if I were to type challenge, print challenge again, I would not see the new data set that this has created. Rather, I would just see what was originally there, because this merely just prints the operation to the console. It does not save it to the data. So the only way to save it to the original variable is that we have to assign it back. So over here we see an example where we assign the new data back onto this initial variable, and that completes this saving of data. So in most languages, assignment is the only way to save data. So just bear that in mind. Alright, I have come to the end of this tutorial part. I thank you all for watching. If you have any comments, feel free to leave them in the comment section below. If there's anything that I said or did that is not correct, do also correct me in the comment section below. I too am a beginner and would be most appreciative of experienced and more senior advice. Till then, take care and I'll see you next time.